In this video, we study the reliable broadcast problem with the goal of minimizing the communication complexity. We will explain all these technical terms in due time. We are given a distributed system comprising a set of nodes, all of which can interact directly by exchanging messages. One node is the current sender, that is, this node wants to broadcast a certain message, in the example the value 8, to all other nodes. The sender can simply send the value to all other nodes and, if all goes well, every node receives the message and the broadcast concludes successfully. However, in practice, there might be failures. There could be simple crash failures where nodes suddenly stop functioning, or Byzantine failures, that is, arbitrary failures including malicious behavior. It is much harder to implement a useful broadcast routine that delivers messages reliably if there can be such failures. When we speak of reliable broadcast, we mean that the broadcast must have specific properties that are guaranteed to hold, even in the presence of faults. The properties of reliable broadcast are the following. A reliable broadcast protocol must have the agreement property. That is, if messages are delivered, they must all be the same message. The second property is called totality. The property says that if a correct node delivers a value, it may take some time but the message is eventually also delivered at all other correct nodes. The third property is the validity property, which says that if the sender is a correct node and it sends some value x, then exactly this value will eventually be delivered at every correct node. What if the sender is faulty? In this case, a message may or may not be delivered but no guarantees can be made. Lastly, the integrity property says that at most one message can be delivered in every protocol execution. In practice, different instances of the protocol are used to deliver multiple messages. Note that the integrity property often includes the requirement that any delivered message must have been broadcast. Since this requirement is often satisfied trivially when the protocol has all other properties, we will not discuss it in this video. It can be shown that reliable broadcast is only possible if the maximum number of Byzantine failures f is strictly less than a third of the number of nodes. We assume throughout this video that this bound on the number of failures holds. A well-known reliable broadcast algorithm uses erasure coding and Merkle proofs to broadcast messages reliably and efficiently. It basically works as follows. In the first round, before sending any messages, the sender encodes the message using erasure coding, creating exactly n fragments, where n is the number of nodes. Note that the number is 4 in this example. The message itself consists of f+1 symbols, which is 2 in the example. Note that a message of arbitrary size can be used in practice by considering it a sequence of f+1 symbols. Each group of f+1 symbols can then be mapped to n symbols. We keep things simple here and say that the message itself consists of f+1 symbols as mentioned before. So, given a message, the sender encodes it into n fragments. The encoding ensures that any f+1 fragment suffice to reconstruct the message. The sender then sends one fragment to each of the nodes, including one to itself. We assume that all nodes and fragments are numbered, so it is clear which fragment should go to which node. All nodes store the received fragment. Since there are 4 nodes, the algorithm must be able to handle one node failure. We assume that node 4 crashes at this stage. In round 2, each node sends the received fragment to all other nodes. The rules of the algorithm are the following. If f+1 fragments are received, which is enough to recover the message, a node decodes the message and then computes all fragments, just like the sender did in the beginning. So, after this step, a node locally stores not only the message m but also all fragments. The second rule says that a node broadcasts its fragment as soon as the node gets it. A node may get the fragment in the first round from the sender directly, or it might get it by encoding the message into fragments once the node has the message. The third and final rule says that a node that receives n-f fragments delivers the message m and terminates. Note that n-f is greater than f+1, so the node must have message m already. This is the entire algorithm. The communication complexity of an algorithm is the number of bits that all correct nodes send together in the worst case. Since all nodes send fragments, we first need to determine the size of a fragment. Since k symbols are mapped to n symbols and k is f+1, which is about n divided by 3, the size blows up by a factor of 3. This means that the size of a fragment is about 3 times the message size divided by n. The additional term, h times log n, is the size of the Merkle proof, which is stated here for the sake of completeness. We do not discuss this term further as it is not very important because we focus on broadcasting large messages and this term does not depend on the message size. Since every node sends its fragment to all other nodes, the communication complexity is roughly n squared times the size of a fragment. Plugging in the fragment size, we see that the communication complexity is 3 times n times the message size, plus some term independent of the message size. This is a nice result considering that n times the message size must be sent in any case. But one might still wonder, can we do better? The answer is yes. We will now briefly discuss how this can be done. We will improve the communication complexity by changing a few things. First, we require that 2f plus 1 out of n fragments are required to decode the message. While more fragments need to be collected now, the advantage is that the fragment size is cut in half, so there is now only a 50% overhead due to the use of erasure coding. We also need to change the algorithm so that it works with this new message encoding. The first and the second round are basically the same. In the first round, the sender sends each node a specific fragment, and in the second round each node broadcasts the received fragment. However, the rules of the algorithm must be adapted. The first rule says that when at least 2f plus 1 fragments have been received, the node recovers the message and then recomputes all the fragments. The second rule remains unchanged, which says that a node broadcasts its fragment if it hasn't done so before. The third step is the crucial trick that makes the algorithm work. For any node I from which no fragment was received, send the fragment that node I should have received from the sender to node I. Note that there can be only f such nodes as 2f plus 1 fragments must have been received. Once these steps are performed, the message is delivered and the node can terminate the execution. Let's check whether this algorithm has all the required properties. The arguments for both agreement and integrity stay basically the same, so we will not cover them here. Instead, let's show that the other two properties still hold, starting with totality. The totality property says that if a correct node delivers a message, other correct nodes must eventually deliver the message as well. Here we use the trick. If V delivers the message, V must first send a fragment to each node from which it did not receive a fragment. This step guarantees that all correct nodes eventually receive and then broadcast their fragments. It follows that all correct nodes will eventually receive at least n-f fragments and deliver the message as well. As far as validity is concerned, the correct sender sends the fragments to all other nodes, which are then broadcast at least by all the correct nodes. It follows again that each correct node receives at least n-f fragments and delivers the message. Having verified that the algorithm is correct, let's analyze the communication complexity of this algorithm. As mentioned before, the size of a fragment is now 1.5 times the message size divided by n. Every node sends its fragment to every other node. Moreover, every node sends at most f fragments to nodes from which it did not receive a fragment. Since f is less than n, divided by 3, the communication complexity increases by at most 1/3. Plugging in the fragment size, we see that the communication complexity is now only 2 times n times the message size. This is a nice improvement, considering the simplicity of the changes that are required to achieve this communication complexity. We can again ask ourselves if we can do even better. And again, the answer is yes. There is a more complicated algorithm that achieves an overhead factor of only 1.5. It can also be shown that 1.5 is actually the best possible bound under some assumptions. But we are happy with the result that we achieved here and leave it at that. Let's summarize what we've learned. We discussed reliable broadcast, which has 4 properties: agreement, totality, validity, and integrity. We started with an erasure coding-based algorithm that achieves an overhead factor of 3. With just a few changes, we managed to reduce this overhead factor to 2. It is also good to know that the communication complexity can be further reduced to a factor of 1.5 using a more complex algorithm. Thanks for watching.